My name is Jane Allwatch, and I work for the South African National Space Agency. And I'll be co-chairing with our colleague from the European Space Agency, Philip. I would like, first of all, to bring you greetings from my CEO and the staff of South African National Space Agency. And for those of you who have heard SANSA for the first time, SANSA is a very young name, but it has this long history of space science that spans more than 8 years in total. Before its formation, and what comprises it was the old CSIR Satellite Application Center and the Hermanus Magnetic Observatory, that is here in Cape Town. Currently, SANSA has got 4 divisions or directorates: Earth Observation, Space Engineering, Space Operations, and Space Science. And in addition to that, it also has Human Capital Development and Science Advancement as its own cross-cutting focus areas. The Earth Observation Directorate, which is represented here by me and some of the staff members, has got lots of national and international projects, and all of them fit into their core goal, which is to apply satellite data and remote sensing to improve livelihoods, to reduce poverty, and also to manage natural disasters. Please next time come and visit us when you come to South Africa, and you'll see what are things that we are involved in. So with those few words, I would like to wish you very good discussions and hand over now to my colleague who will introduce the panelists and also start the meeting. Thank you.
Good morning. So we will start this session with an overview from the European Space Agency. I'm Philippe Bally from ESA. I'm co-chairing the session with SANSA. I'm very happy to be here with you, and I'm grateful to the World Bank for this opportunity. And my presentation will start now, and it's a rapid overview of the capabilities of EO for disaster risk management. Thank you. Okay. So I translate with this. All right. So the purpose of my presentation is to give you an overview of what a satellite EO can do to support activities in disaster risk management. And this is a rapid presentation of 10 minutes, because then I will give the floor to panelists that are all partners from Africa with a specialty in different types of hazards that will give more illustrated examples of applications of EO. First of all, the European Space Agency is a technical development agency. We build satellites. We are not in DRM, we are not in risk management, and we are in technology and science. We take part to international collaborations in the field of risk management since many years, and ESA is one of the founders of the International Charter, Space and Major Disasters. And we also take part to a SEOS activity. SEOS is the Committee of Earth Observation Systems, and we collaborate with 9 other space agencies on an ad hoc study team to look at what we should do to improve the use of satellite EO for disaster risk management. That SEOS activity started in November 2011 and will deliver its first study report in September 2012. So it's a framework of different international collaborations where ESA is trying to look at how we can better use satellite data for risk management. Further to these examples, ESA is also collaborating with the World Bank, and there will be a dedicated presentation with my partners from World Bank just after my presentation. The capabilities of satellite EO for DRM are represented on this slide. The circle represents all the phases of disaster risk management, and the blue items are the different categories, and the red items are examples of EO products or services that are available today. Not R&D, but things that at least have a prototype that has been tested and we know it works. So for emergency response, you have crisis mapping, rapid mapping, damage assessment, situation mapping. We will see a few examples. For prevention, preparedness, recovery, reconstruction, which is a very broad range of different activities for different hazard types, there are different types of products available. And I think the bulk of the content here is risk assessment products able to better understand the hazards and their impact, and to prevent hazards. For all phases, there are generic products that can fit different types of applications. For example, land use products, or asset mapping, products to support asset modeling, and so on. To make a long story short, I could say Satellite TO can help science and operational users. There are two facets, two types of users: those who want to understand the hazards and to study them, and those who are in the operational applications. And this goes into two main categories: exposure, asset mapping, asset modeling, so people who are concerned with the asset at risk, and here a very broad range of EO products can contribute. And the second category is people who are concerned with the mapping of the hazard itself or the impact of the hazard. Here you have different examples of applications that are either scientific or operational. To go quickly, I will show you three examples. Number one, in the first category for asset mapping, asset modeling, a typical example is a satellite-based map of buildings in the region, so that the elements that are exposed to risk are represented with an objective and synoptic method thanks to satellite imagery. The bottom left example was produced in the time of a crisis during the impact of the South Asian earthquake of 2005, and was used by the UN relief teams as they were going to the Kashmir area to support local people. The top right example is an example developed in a pilot project with the World Bank, and looking at land use in Cambodia, and to look at the areas exposed to flood risk. That example is an example of hazard information derived from satellite data that is not for operational user, it's an example for science user. With this example, you have the longest interferogram ever produced for seismic hazard mapping. It's several hundred kilometers, just after the Japanese disasters of March 2011, and it shows 2.4 meter displacement of the ground surface. And this is not used for civil protection to support relief operation. This is used for scientists that try to assess, characterize, or model the earthquake phenomena itself. Another example of a very similar technique that is based on radar imagery used for operational users. This example is with the civil protection in the south of Italy, and that was used to update a prevention risk map, and it was used to modify the priorities for a settlement in the development of this urban agglomeration, a peri-urban agglomeration. It could show a new estimation of unstable areas in a village exposed to landslide risk. So in that example, the satellite data is used by operational users. It is fully validated, and it is used operationally. Concerning a rapid response to disasters, the most available and operational capacity that is in place today is the International Charter Space and Major Disaster. It was set up 10 years ago, and today it has 14 members, 14 space agencies, and the definition and role of the Charter is extremely simple. It is a unified system to coordinate emergency tasking, rush tasking of satellites to provide very quickly a large series of data to support the immediate response phase. So it's a virtual constellation of satellites, and the simple purpose is to bypass all the commercial or scientific orders and make priority tasking. The data are then given at no cost to users. The main users of the Charter are civil protection authorities and the UN via two intermediates. There are very simple requirements for the type of services needed for the Charter. It's primarily very quickly provide a reference mapping of the area. Within 6 hours, provide a reference map, a background space map. And secondly, every day, provide a zonation of the impact of the hazard on a daily basis. That's what the users say they want. The type of hazard that are addressed with the Charter are not all types of hazard. It's only focused on a rapid onset scenario, because a slow onset scenario does not require to bypass commercial or scientific orders. The Charter is there when you have an event that is not planned, not plannable, sudden, and then you just stop all the orders and make images quickly. It means that drought, for example, is not a good case for the Charter. The Charter would not be useful, and there are better mechanisms to address drought. But if you have landslide, volcanic eruption, or floods, the Charter is a good mechanism. This slide is showing very quickly the types of hazard that we understand are pertinent to Africa, but other presenters in this session will give more precise information on this. But I understand that hydrometeorological hazards are important, more important than geohazards, and epidemic and insect infestation are issues for Africa. And this is the histogram of the charter activations over Africa. So the blue bar shows how many mass disasters have been recorded according to EMDAT from CRED in Brussels, and the red bars show the charter activations and the list of countries for which there was a charter activation. This is showing the types of hazards for the charter activations, and we can see easily that number one is floods. Floods in many places of Africa correspond to different charter events in the last 10 years of the charter. So the way to access the charter is either for an authorized user, which is a national civil protection, or via the UN with UNOSA in Vienna, or UNITA UNOSAT in Geneva, or an authorized user triggers for another country. For example, for the earthquake of Bam in Iran, Germany has sent relief teams to support relief operations in Iran, and they trigger the charter. So the charter can be triggered by an authorized user for another country. Further to this, a resolution has been adopted by the Charter 1 year ago in London, and this resolution is about universal access. The resolution means that any country in the world should have access, direct access to the Charter. So far, the authorized users of the Charter are civil protection authorities in the countries of Charter members. That was a decision at the start of the creation of the Charter. With universal access, the intention is that any civil protection authority in the world should have direct access to the Charter, provided some basic criteria are met. The basic criteria are very simple. The entity must be a national disaster management authority. It must have the capacity to download and use maps, otherwise that would not be useful. And third, it must be able to formulate the request for the Charter activation using English. That's a very simple and quick step in the activation. You have to say what is the disaster type, the time and location, and with this very basic information, we can trigger the system. The rest of the communication during the job is done in different languages, and we select a project manager for an activation according to jet lag, according to the culture and language, but the very start requires to speak English or to write English. So these are very simple criteria, and with this we are trying to open the door to have more users with the direct access, with primary focus on national users. This is the list of countries in Africa that have been consulted via the formal consultation managed by the Charter through the European Space Agency, and there are other Charter members participating to actions with national users that could be potential direct users in the future. Now I'm showing you a few illustrations of how satellite data are used to generate services, either for operations or for science, in the context of risk management. First of all, with the October 2004 Asian disaster in the Kashmir area, this map is using satellite images and is able to detect unstable ground, landslides, and is able to unmix landslides that were already occurred at the time of the earthquake and landslides that are triggered by the earthquake. So there is image analysis and analysis of time series to identify, detect, and measure the impact of hazards that will affect how the relief teams can go and help people to the ground. Many roads were blocked by the landslides, and that map was quite useful. It was actually given put in the hands of Kofi Annan at the time of a donors meeting in Geneva. It has been a quite useful product in the field as well. Now, looking not at emergency response, but prevention, which is much broader, much more demanding, and a big area, satellite data can be used to complement work done with in-situ information and the collection of in-situ data to do a deep analysis to better understand the mechanism of a hazard. In this example, that will be detailed further in the next presentation with the World Bank, we have satellite measurements of terrain deformation with millimetric accuracy using a very dense archive of more than 15 years of data and different satellites. In this kind of example, we have point measurements that are very close spatially and that cover a very long time span that give precise measurement of vertical deformation of the ground. This is a key issue in subsidence areas, especially in coastal lowland. In this example with Jakarta, Jakarta is exposed to flood risk, but also has subsidence problems that are related to groundwater management, and measuring precisely the ground deformation is an important aspect of the work. Looking into details with new satellites from national missions like Cosmo in Italy, Cosmo SkyMed, you have a very dense population of measurement points with millimetric precision data that allow to better characterize the terrain deformation. All the points in red here, they show subsidence pattern. All that is because these civilian satellites used for risk management have an ability to generate very dense and very wide archives of data. These two maps show ESA's Envisat satellite archive and the German TerraSAR X-band archive. And in both cases, you see a very wide coverage spatially, but also in time, you have a very dense coverage. With ERS and Envisat, you have 15 years of data, which is the most dense archive of civilian data. This map is showing you just the example of radar images, radar sensors from radar satellites, and you see a very wide range of different sensors. And within the next months and years, you will see more sensors coming in and very large volume of data being available on a very frequent basis. So within a few years, we will be able to get almost daily coverage with radar data. In the case of Europe, we are building a family of satellites called Sentinel in the framework of the European Union's initiative GMES, Global Monitoring for Environment and Security. And specifically for disaster risk management, Sentinel-1 will be very useful because it will provide a 12-day revisit coverage with high-resolution radar data. And there will be two Sentinel-1, 1A, 1B. Sentinel-2 will provide 10-meter images in the optical domain, and we will achieve 100% coverage of the land surfaces. All the data from the Sentinels will be freely available to users. With Sentinel-2, you will get data all over the place without any restriction. For Sentinel-1, the availability of the data will be related to the duty cycle of the mission, and not the full orbit can be operated because of the large volumes of data, but the target is that it will be between 25 and 30% of the orbit that will have acquisitions to give data to users. So it will be monster satellites doing carpet coverages. As a take-home message from this overview, for the crisis response, there is an international system capacity that is available, and the base of users is growing, and more users will have direct access. And we can see that the services derived from the Charter are being adopted by the civil protections. Access for users should be improved, so we work on this universal access, and particular focus is on Africa, where many countries do not have direct access. Concerning risk prevention and mitigation, the capacity devoted to DRM users are established, are being developed. There are many users who have already adopted services using satellite EO, especially in Europe. For example, more than 50 geological surveys have signed service level agreements to get satellite-based measurement for geohazard risk, for example, for landslide risk. It's quite embryonic in Africa, and the level of use of satellite data for hazard risk prevention is quite limited today, and there is a high potential for doing more with satellite data for risks in Africa. And last message is that to deliver data and value-adding services requires to address a range of different challenges, like the cost, access to data, the cost of the service, the capacity to do data processing, thematic knowledge, because the precise measurement from the satellite data is not enough without geological knowledge or hydrological knowledge with an expert user or an intermediate, a specialist. And then raising awareness. Many users are not aware of the capacity of EO, they just don't know what it can do. And capacity building is needed in some places where the ability to exploit the data needs to be developed further. So thank you for this, for listening to this overview. And I would now like to give the floor to the next presentation from Anna Berzikowska. Except if you have any question on this presentation, the best would be that we devote some time at the end of the presentation for a discussion on the sum of the presentations. So if there is no question, I will invite Anna to come along. Thank you.
Morning, it's a pleasure to be here. I'm actually filling in for Anthony Biggio, who sadly couldn't be here. But I'm working on his team, and Tony is leading an initiative at the World Bank, which is called Earth Observation for Development. And basically, the aim of this program, of this initiative, is to mainstream, help to sorry, is it better? The aim of this initiative is to mainstream the use of Earth observation information in the World Bank in the areas relevant to sustainable development, and that includes water resources management, agriculture, forestry, climate change, and disaster risk management. One of the first activities that we had in the pipeline in this initiative was actually a collaboration with the European Space Agency, and that's how it all started. My presentation will focus on the results of this collaboration in the area of disaster risk management and what was the World Bank experience in actually using the Earth observation-based services in the World Bank projects. So being in this conference, you already get a clear sense that application of new technologies, including Earth observation, remote sensing, is actually at the heart of disaster risk management practice at the World Bank. And this field has been growing very rapidly over the years around the world. There are new satellite capabilities and new players working in this field. A number of countries that actually operate the satellites on their own is something like 20. And the fact that we are in this session and being hosted jointly by the European Space Agency and South African Space Agency actually is a very good example of how these exciting developments are spreading over to the developing countries as well. The awareness of the possibilities with Earth observation at the World Bank has grown very rapidly with a new set of partnerships that the World Bank had developed with specialized organizations in this field. And that includes Japanese Space Agency that did some exciting work on climate change adaptation in the Latin America region. NASA is working with the World Bank in mainstreaming the use of remote sensing in water resources management in North Africa, Middle Eastern countries. And we have the collaboration with the European Space Agency, which is actually cross-cutting across many areas of collaboration. You can find more information on this website, and we have a progress report which details this collaboration. The interesting thing to know is that half of the 15 pilot projects that ESA has developed for the World Bank, half of them are actually addressing disaster risk. I will come back to that slide later on because it just shows the next step of collaboration with ESA. But first, let me tell you a little bit more about those projects which we have developed over the last 2 years. So 6 pilot projects spread across 3 regions of the World Bank: Latin America, East Asia Pacific, and Middle East and North Africa. Developing different kind of projects, starting with the digital elevation models and land use products, and finishing with precise terrain motion mapping and flood simulations. In this collaboration, the way it worked was that once the products were developed, they were immediately transferred to the local authorities, local users in these countries. So, for example, in case of Rio de Janeiro, once the project was completed, the World Bank project managers transferred the knowledge to the operational center for disaster response of Rio de Janeiro and Rio de Janeiro geological services. In case of Jakarta, we are working with the Department of Public Works of the local government, DKI. 2 things were highlighted very quickly once we were in the process of implementing those projects. And the first one was that the capacity to work with this information varies depending from country to country and from city to city. And there is a need to build further the capacity to work with this information, and also to provide adequate information technologies, including geospatial information tools and geospatial infrastructure, and also to develop this sort of infrastructure to work with geospatial information at the World Bank. Because the bank did not have, before this collaboration started, the bank did not have integrated internal GIS portal, and we actually developed it specifically to serve better these projects. Let me give you practical examples of what was actually achieved. Land subsidence in Jakarta, actually quite well-known phenomenon. And the map on the left side shows you the type of information that the local government was working with when addressing the issues with land subsidence. And there's no legend here, but some of the areas here has actually sunk more than 1.5 meter over the last 30 years. Interesting thing to know is what kind of information has, what kind of dialogue started after ESA has developed this new pilot study using satellite interferometry and providing more detailed information on land subsidence. And the first thing that you notice is that there is a dramatic improvement in the resolution and detail. So it is possible to detect trends which were not evaluated by in situ techniques. And also with the use of, because there were two sets of products, and with the use of higher resolution radar imagery, it was possible to detect motion using on the level of the single infrastructure element. And these technical possibilities are very exciting, so the projects were really actually very well received by the local government. But what was even more exciting is the power of persuasion that came along with it. So it turned out that this method is not only very effective when it comes to measuring of subsidence, but also communicate the risks that face cities. And the TTL who was working on this project, the project manager at the World Bank, said that if this measuring subsidence in Jakarta is complex technically, it is even more complex institutionally, because it requires bringing many authorities and many stakeholders around the table to address the common problem. And he said that when he was working on addressing flood risk management in the city of Jakarta, it took him 3 years to bring together the stakeholders to talk about how to improve the flood management system in the city. And with these maps developed for subsidence, it took him 3 weeks to get everyone interested in this type of information. So immediately, the port authorities, local transport agency, the agency working in water resources management, managing buildings and settlements, were very interested in using this information, having access to this information. And why was it so useful for the bank? Because having this information at hand, it was possible for the project managers to go to the port authority and say, this is what is happening on your side of the fence. It was possible for them to go to the local electricity company and say that these are the trends, long-term trends, this is what is happening to your infrastructure. And the project was actually quite successful, and right now this information is going to be used for law enforcement in controlling the stability of the buildings which are higher, 5 floors and higher. It's going to be used to monitor the stability of Jakarta coastal defense. It's going to be used for for advocacy for further spatial planning in the city, and of course to control groundwater extraction, because that's the main cause of land subsidence in Jakarta. That's one example. We have 6 projects in the pipeline, and there's no time to go into details, but I'd like to highlight a couple of things. First of all, ESA has developed this type of project for 7 cities. In the world. 2 minutes left. Whether these are building maps, using Earth observation building maps of infrastructure and assets, or building exposure information. Actually, there's a very interesting slide here showing is it working? It's not working. But this is a simulation of the Lahar floods, which was developed for Yogyakarta. Oh, I think it is.
Video.
We can actually skip to the next slide. This information is actually Earth observation based information is actually very useful for disaster risk assessment, and that was one of the key lessons that we learned at the bank. But of course, this is not a silver bullet. And you can use Earth observation to derive very useful information, especially in cases when no other information is available from other sources. With the use of ground information, it can be complemented with the information collected by in situ techniques. It can become a very powerful tool. sorry for that. We have some technical problems.
Is there a video?
You can just skip to another next slide.
Can we just open the video in here?
No, we don't. Just
Leave
skip.
the video.
No,
Oh.
just if I can go back to the power.
The PowerPoint's like crashed. Is it?
Close the PowerPoint.
I think it froze. Let me just conclude because we have no time. We are right now entering the second phase of collaboration with European Space Agency and like to do more bigger programs, more substantial programs in a number of areas that has been selected by the World Bank as the priority. And these are oceans, forestry, disaster risk management, and fragile states. So we are looking forward to this collaboration and we're looking forward to the use of Earth observation at the World Bank because really managing the global programs on natural resources management and disaster risk really requires Earth observation as a necessity. So thank you very much and I'll give the floor to the next presenters.
Yeah. It's just it's freezing though.
Yes. Close PowerPoint
just
and close VLC. And home and PowerPoint as well. It will close and it will. Yes, just end now.
Yeah.
Okay.
It's this one.
Good morning, ladies and gentlemen. It's my pleasure to make this presentation, and in a way it's also amusing that I have to make this presentation about EO, because I'm not at all an EO expert. I'm a hydrologist or a civil engineer, like it used to be called. One of the reasons that we have discovered in Namibia the use of EO is the experiences we had with floods in Namibia. And that in a way, there's something with this technology. Oh, that in a way is also amusing that we in Namibia have these floods. I depicted here the position of Namibia in Africa. If you see the top right map, it shows that Namibia is in fact a desert or a semi-desert with very few rivers. Now, the water we get that generates these floods is in fact a gift or a donation from the neighboring countries in the south or in the north, or river systems that cause the floods are either sitting in the south with the Orange River coming from South Africa, or the rivers in the north coming from Angola and Zambia, the Kavango River, the Zambezi River, the Kunene River, and the Kuvelai River. And that in a way already explains why we have this great need for Earth observations. Whatever monitoring systems hydrologists can want to put up, they want to put them up in the ground. And we can hardly invade our mighty neighbors to put up our monitoring systems there. It's also interesting to quickly look at the strange hydrological trends we've had in Namibia for the past 10 and the past 5 years. We didn't really know that phenomenon of floods up to 2006. And then we suddenly got in all these rivers a cascade of floods, the highest on record or the highest since 40 or 50 years. I've tried here to make a bit of a statistical overview. Now, there's different theories for that. Of course, the people who make money out of climate change, they will all say it's because of climate change, but it doesn't matter. We have to live with the consequences. For people living in a dry country, the consequences of flood are a bit extreme because of the element of surprise. People don't expect that. Even if you give warning, they still don't believe it until the water is there, because the water doesn't come in most cases from local rains, but from rains that are 500 kilometers apart and that occurred 2 or 3 weeks before. Now, the balance for Namibia in 2009, the World Bank came and did an assessment of the damage, and in absolute terms, these numbers may not look very impressive. They are not impressive at all in comparison with things that happen in Pakistan and in Myanmar, but in terms of the size of Namibia, these numbers are quite high. About 30% of our population got affected, for instance. Now, I was asked to give a couple of examples on how to use EO in hydrology and specifically in flood modeling and flood management. Now, the first obvious illustration is something that has been going on for a long time, since the 60s, with the advent of the satellites, and that is that satellites are being used to monitor the weather and to monitor the clouds, and in a way to monitor the rainfalls. And so the first application that we use, and that is in particular important for us because in a way we want to spy on what's happening in the neighboring countries, is that we make use of satellite images to get monitoring of the weather condition and also monitoring of the rainfall. Now, I will show some images now, but the main thing with this monitoring of the rainfall is it is based on monitoring of cloud physics. And the estimates that are made for rainfall are indirect. They are based, say, for convective storms, they are based on monitoring in the infrared band, monitoring of the cloud temperature, which is a measure for the development of the rainfall storms and a measure for the intensity of the rainfall storms. But what is often forgotten is that at some stage one needs to do ground calibration. And the disturbing fact that we see is that there's many more of these systems coming in practice. A lot of them are sitting on the internet. They produce nice maps, but what people forget is about the need for ground calibration. The most known one is probably the TRIM satellite. This is an example of 6 of the systems that we currently use in Namibia. There's top left the UMETSAT. In the middle is the flash flood guidance systems. Top right is a system that UNESCO has made. And all these maps seem to give very accurate rainfall estimates. In reality, they don't. We find that there's errors of up to 200% in the estimates that these images produce. And that has nothing to do with the science that is behind it. It's got to do with 2 factors. The one is the absence of information on the ground to do the calibration, to do the validation. And secondly, say the disinterest of people to do this validation. People like to make these maps, but they don't like to do this tedious work of calibrating them and finding that it's maybe not so good. For hydrologists, the bread and butter issue is always about river flow monitoring. Now, river flow monitoring on the ground is very easy. You have water level recorders in your rivers, and they give then warning for the people downstream. Satellite observations, EO observations, have started to look in this matter, and there are attempts in different directions. The one is, and I'll show a slide of that, but the one is to directly monitor the water levels like satellites are used to construct terrain models. There are challenges with that. One challenge, of course, is the accuracy. But another challenge is the frequency, and a challenge is often the location where you want that measurement, or the direction of the river that you want to measure. The alternative approach is something that has been tried, or that has been done extensively in China, where satellites are used not to try to measure the height of the river, the level of the river, but to try to measure in a fixed location the flow width of the river, which is then indirectly related to the flow and to the flow magnitude. The most successful thing that we have seen, or that we have used for our condition, is something, okay, in America it's probably known as the Bob Breckenridge system, the Dartmouth Flood Observatory. We in Africa know it better from the Joint Research Center from the European Union. It is an indirect measurement of the flow magnitude that is based on a measurement of the moisture in a pixel, in a very large pixel. So the system is based on an overflight of a satellite, and every time the moisture in a certain reference pixel is measured. And as the river rises, the water surface area increases, and the moisture signal of that pixel increases. So it is a very indirect measure. It depends on a lot of things, whether you have suitable locations. If you have a river in a narrow valley, for instance, the water surface doesn't decrease much, doesn't change much when the depth varies, and you will not pick up much. If you have local rainfall that creates local pools, you will kind of get false signals. Now, in some places, okay, this is first an example of interferometry, where people try to measure directly the water level. The blue line is the hydrograph as it is observed on the ground. The green points show the estimates from a radar satellite for the water level at that point. At this stage, we don't consider that system very operational. One is, well, there is still a problem with the accuracy, say, but there is especially a problem with the frequency of the observations. You can't get enough points in time. Now, this is the system that we then said works a bit better based on repeated measurements of the soil moisture. The map bottom left shows the pixels that the European Union have put, the Joint Research Center have put up for us, where they measure every 12 hours the soil moisture. And to the right, top and bottom, you see some of the hydrographs that are constructed from that. Now, these hydrographs are not in the conventional sense, as we understand it, that they measure the levels or the flows. They measure a dimensionless flood magnitude number. But that can be, in a way, converted to levels or to hydrographs. The third application we have then, and I think that's the one that is well known, is the flood mapping. There's many applications of that. I'm showing some examples here. MODIS images, a Terrasar image at the bottom. Bottom left, bottom right is a radar set one. Top right is QuickBird one. There's many applications of that. They have to rely often on radar images because of the penetration of the clouds. And we did a lot of ground validation on that, because we hydrologists don't believe these satellite things at face value. But you see, for instance, to the top right, we have radar images with the flood mask, and the red crosses are the ground GPS readings. At the bottom, that is a stretch of river about 100 kilometers long, where we also got a radar set image. It's blue. Maybe you think it's a photo, but it's in processed radar images. The red points are GPS readings. So the technique, from our perspective, is fairly reliable. And then the last application that we as hydrologists are starting to look at is to set up a model for flood forecasting. the input for any flood forecasting model is the rainfall, and in a way that you can obtain from satellite images. The second important input for a flood forecasting model is the soil moisture, which is very difficult to measure. And it's very difficult to measure because it's not a point measurement that you must take, but like for rainfall, you must get an aerial measurement. And we found that there are systems that can measure that soil moisture, and so we are busy putting that in, well, it's an American model. It doesn't matter because all the hydrological models work on that water balance for the soil. So that in short is what I want to tell you. Now there is one hopeful thing in all these issues. We entered this scene of EOS hydrologists not at all knowing what EO was about. And we found an amazing level of international support for us. Maybe it's because some of the space agencies want to demonstrate their products, but not only through the space charter that Mr. Bailly illustrated, but also through, say, voluntary support from commercial organizations. They were all very keen to assist us, not only, say, during the disaster, but also during the follow-up and the preparation for the next disaster, if it would come. And I would like to encourage people to explore these avenues. We in Africa have now SANSA, for instance. We didn't know they existed. They certainly also offered support. And that is a hope-giving phenomenon. We always hear about the high cost of satellite images, and there is a high cost in a way. There's a high cost in acquiring the images. There's maybe a high cost in getting the computers and the internet. And there's maybe a high cost in training, but in practice, we found that once you knock at that door is put open, and you are invited in. And the issue that you are asking stupid questions, for instance, is not held against you. And that is something I want to say from our perspective. Entering this scene, we did it with great hesitation because of everybody saying it's costly and it's too difficult and you will never manage it and the people in your country will never master that art. And we found that the opposite has happened. We suddenly discovered that the young people are capable of doing that. They need a bit of training, but we have advanced. If I compare where we stood 5 years ago, we have advanced a lot and we are still advancing. Thank you very much.
Good morning, ladies and gentlemen. My presentation looks at SANSA's contributions towards disaster and risk management. And Jane has already alluded to some of the activities which are already taking place within SANSA. So I'll just continue that discussion within the context of disaster management. Before I look at what SANSA is contributing towards disaster management, I thought it was very important for me to first examine what is the definition of disaster management so that we just go to the basics and be able to know in what capacity or in what aspect of disaster management SANSA is contributing in. And one of the definitions which I got from the Disaster Management Act of South Africa, Act 57 of 2002, was that disaster management is continuous and integrated, multi-sectorial, multidisciplinary process of planning and implementing of measures aimed at preventing or reducing the risk of disasters, mitigating the severity or consequence of disasters, emergency preparedness, a rapid and effective response to disasters, and a post-disaster recovery and rehabilitation. And looking at this definition, if you look at all the aspects which are within that definition, and you look at what Earth observation can contribute in, I almost realized it almost contributes in every component of that definition. And I've therefore moved on to say that in this regard, where does observation play a part? Earth observation is central in various aspects of disaster management, according to the definition which I've given out there, in terms of the monitoring, hazard assessment, vulnerability and disaster assessment, contingent planning, and in developing reporting systems, whereby you have got maps. As you issue out a report, you have got a map of which shows the exact spatial extents of the disaster, and obviously in the development of early warning systems. Then where else can Earth observation contribute? Obviously in near real-time observations, where the satellite is continuously monitoring a particular area and feeding information into decision-making, into decision support systems. And one area as well is obviously in the provision of spatial information or the geographical information which really depicts the geographical extent of the disaster wherever it has occurred. For instance, when you've got flooding, you would want to know the exact spatial extents of that flood so that you're able to provide relief efforts in time. Then the slide takes you through just the geographical distribution of some of the floods which are occurring within South Africa. You would find out South Africa is also prone to a number of disaster incidences, particularly floods and fires. We would say, I think, in terms of our fire rating, I think it's quite high for South Africa, as well as flood. I think they are the two major disasters which dominate the South African landscape. Then this slide gives you an overview of some of the thematic areas which are within SANSA. SANSA has got 6 thematic areas, and apparently disaster management is actually one of them. Why is it so important to us? Because we realize, I think, disaster management, given its the kind of damage which it does to infrastructure and the kind of impact which it has got on livelihoods, we realize it is one of the areas where you can really demonstrate the value of Earth observation technology. And in that way, it's even able to justify the kind of investments which get into Earth observation. And one aspect, even if you look at those 6 operational areas, you also realize disaster management itself is cross-cutting within those particular thematic areas as well, because if you look at environmental management, whenever floods occur, I mean, this is an environmental aspect. There is, if you look at planning and development, if you are looking at infrastructure, floods tend to have devastating effect on infrastructure. Earthquakes have got devastating effect on infrastructure as well. So therefore, the disaster management tends to cross-cut across all of those thematic areas and even issues of national security as well. Then this slide just demonstrates some of the contributions which we have made. Hido from Namibia was just talking about SANSA's contribution towards some of the efforts which they're doing in Namibia. And this image here shows you the Sumbandla set image, which was acquired over Okashati in Namibia. That was sometime in April last year when there was flooding, and we were able to give them this image in almost near real time to indicate to them the spatial extents of the flooding. So this image on your left just shows you what it was before the flood, then the after image after the flooding. And here we're just also demonstrating some of the efforts which we have done in flooding, where we're using spot imagery to show the spatial extent of the flooding and what you can use this imagery for to actually indicate the real areas which have been affected by the floods. And if one needs to offer any form of logistical support to those particular areas, then one is in a position to know which areas have been affected. And if you are going to do post-disaster risk assessment, you are in a better position to to really quantify the exact extent of that flood. This was in the Limpopo River. Then this one, the slide here just shows you some of the activities we've also been doing in supporting disaster management across the globe. This shows you what the Sumbandila image, which was acquired over Japan during the tsunami last year. And as again, it's a South African satellite, Sumbandila, which acquired this image. And there is no pre-process, there isn't any further processing to this kind of imagery, but the extent of the damage which occurred in Japan is quite evident in this slide. So it just goes on to demonstrate the exact value of satellite imagery in disaster management and risk assessment. Then this slide here just indicates to you the ability of Earth observation satellites to detect fires and where they are fires where they are occurring, and to a large extent the damages, the spatial extents as well, in terms of the areas which have been destroyed by fires. We're continuously doing this for farmers within South Africa and for insurance companies, where they would want to know the exact extents of or the amount of destruction which has been caused by a fire. And we do a simple change detection analysis to indicate that in this particular case we show the fire damage map and areas which have been destroyed by fire. This slide takes you through one of the systems which we think is very valuable, where we continuously contribute satellite imagery. It's managed and continuously developed by the Meraka Institute, and it's called the Active Fire Detection System. It's called AFRIS, and it's been widely used within South Africa and other parts of Africa to continuously monitor fires in almost near real time. And it's being used extensively by ESCOM, which is the Electricity Distribution Authority in South Africa. And it has been used extensively, and it continues to find value within other African states, whereby whenever a fire takes place, they can indicate to you via SMS where that fire is taking place. And this just goes on to show you how this fire, which is destroying electric pylons, is being detected by the satellite imagery, and it has been very valuable to the local electricity distribution authority here within South Africa. And at one time, it was actually being also within our weather reports, or to indicate the amount of risk, fire risk which is occurring within the country. They would also put it on the news bulletin. Then the slide goes on to indicate as well the value of satellite imagery in also assessing our water resources, because they tend obviously to be highly polluted. And here it shows eutrophication, which is occurring within that river, and usually that could also be having a devastating effect to the people who consume that water. Then obviously our vision as the South African National Space Agency is to continuously contribute to disaster and risk management within the country, and to support disaster management agencies within the country and the region. And we are well aware the National Disaster Management Center has developed a National Disaster Management Information System. And from the architecture of that system, what we intend to do is to continue to have geo-information products developed derived from satellite imagery to feed into that particular system, so that it supports all the disaster management efforts which they are trying to do within the country and the region. Then also, before I came to this conference, I was asked then by a team from GEO to say, can you also include some of the activities which are taking place within GEO? It has formed an initiative which is called Africa GEOS, which is an initiative to coordinate and bring about relevant stakeholders and institutions across Africa to contribute to the GEO initiatives in Africa. Because I think ever since the inception of the GEO program, there wasn't a lot of participation from African countries. So this provides a platform to allow African countries to share knowledge and also contribute to these initiatives. And some of the activities which are taking, some of the targets are some regional agencies and training centers within Africa. And some of the achievements which they would want to look at particularly is to coordinate data acquisition for African countries. Then they're also looking at the African Resource and Environmental Management Constellation, the ARMC, the development of Africa GeoSet 1 project, and obviously they will want to continue to contribute to some of the activities which are taking place within Africa, which the European Union is also contributing in, such as the African Monitoring for the Environment and Sustainable Development, and the monitoring of environment and security in Africa, which is a follow-up to the AMESD project. So with that, I thank you, and we hope we will be able to discuss further on some of the activities taking place within SANSA.
Is based in Cairo and cover 57 countries. I'm pleased to present you in a presentation about application of Earth observation data for disaster risk management. We'll focus a little bit more on forest fire, drought, but we will touch also flood and landslides. So let's start with this slide, which shows disaster risk management cycle as it was presented by Philips. It is composed from different phases, which are successive and complementary. And for every phase, we need data and information in order to manage disaster risk. So we have the habit to, and sometimes we need the data in the time, in the best moment. Especially for the case of crisis management, we need the time is important, and we need the data in time. We have the habit to divide this cycle on 3 big phases, which are pre-disaster, during disaster, and after disaster. In the other side, we have space technology, which can contribute significantly to disaster risk management through Earth observation satellite, telecommunication satellite, and positioning satellite. So as you know, Earth observation satellite provide us remote sensed data or satellite images that we can use in order to produce maps in different scales. Telecommunication satellite allowed us to transfer this data and information quickly and everywhere in the world, and positioning system provide us positioning and localization in space. Of course, we will focus more on the Earth observation satellite. And before to go to the application, I would like to start by 2 examples. One, just pre-disaster, before disaster, and the other one after disaster. So one of the most important phases in pre-disaster is risk assessment or multi-risk assessment. So I think you are familiar with this equation, which allowed us to estimate a risk using hazard and vulnerability. And remote sensing data, remote sensing and Earth observation can contribute to the estimation of the 2 aspects. So for the vulnerability, we can produce land use extract the assist, and for the hazard, remote sensing data can estimate some parameters, like for the case of forest fires, combustibility and flammability, the interface between forest and human activities. For the case of drought, humidity, soil ruggedness, land use, etc., etc. So once we have these two parameters, the risk assessment become a piece of cake. The second example that I want to illustrate is the case of damage assessment or just post-disaster analysis. So in order to perform DALA or PDNE, DALA is the damage and loss assessment, and the PDNE is post-disaster need assessment, we need two elements. The exposure, information about the exposure, and information about disaster footprint. So as you know, we have a lot of satellite images, which allows us to extract information and to produce map in different scales and with different legends. So they give us a lot of information about exposures. And in the other hand, through the activation, for example, of International Charter for Disaster and Major Disaster, we can have satellite images just after the disaster, so which allowed us to extract the footprint. We have here an example of forest fire and the other one for flood. So let's start with first application, which focus on forest fires. And the first phase, of course, is pre-disaster. And in the case of forest fire, we can talk about two types of risk: structural risk and conjunctural risk. The structural risk is due to the combination of factors which are more or less stable in time, like topography, aspect, orientation, combustibility of species, etc. And the conjunctural risk is due to the impact, temporal impact of meteorological condition on the forest and vegetation covers. So we have here an example of approach used for conjunctural risk, structural risk assessment. So here the remote sensing or earth observation data contributed, for example, to the updating of forest maps, and also to estimate using, we used also this forest map in order to estimate the combustibility of species. It can contribute also to the cartography of the interface between human activities and the forest. And this interface is very important as they are the source of fire ignitions. And we have here some example of maps that we can produce with different level of risk. In the case of conjunctural risk, of course, the methodology used involve earth observation data, meteorological data concerning speed, wind speed, etc. Here I illustrate to use the contribution or high temporal resolution like NOAA or MODIS through the production of two indexes. The first one is Vegetation Regression Index, which is based on time series analysis of NDVI during the 60 days before, and Vegetation Drought Index, which is based on the analysis of slope between land surface temperature and NDVI. So the integration of this indices with other information like wind speed allowed us to produce maps daily and follow. We have here the case of June 2007, follow daily disaster day by day and make more vigilance in the concerned areas. So during the disaster, the analysis of brightness temperature, we have a lot of algorithms that we can use in order to analyze brightness temperature and extract the active fires or hotspot. It can be threshold algorithm or contextual algorithm or other one. And I illustrate here the case of one of the fires in Chefchaouen province in Morocco. So here we used the NOAA images in order to detect and to follow this fire. Post-disaster, of course, as it was presented, we can extract easily the fire footprint that we can overlay on, for example, map of forest species in order to extract the burned species and estimate the loss, etc. So now we will talk a little bit about drought. This is the map which is produced by IPCC through the analysis of PDSE from 90 to 2002. And the map shows that drought is concerned not all the world, of course, but it takes a disaster dimension in Africa, for example. The PDSI is one of the indices, it's Palmer Drought Severity Index, but in the literature review, we have more than 300 indices. And some of these indices can be extracted from satellite images. So here we have an example of this indices, which is SVI, Standardized Vegetation Index, and which is calculated using NDVI. So it is based on time series analysis of NDVI, and it is based also on the test student analysis. So we have here two maps, one for 2007, which show great and important drought in the east of Morocco, and just a year before, in 2006, we have the same map, but which shows comfortable conditions. So the literature review also showed that a new indices, which is NDWI, normally is different water index, which is very sensitive to water contents. And we have here an example of this indices, which is calculated on the basis of spot vegetation. And the idea is to use this index in order to follow and assess, to monitor in space and time drought. It can be done at level of the country, and it can be also, okay, 2 minutes, at level of the watershed. You have here the example of the spatiotemporal monitoring of the drought phenomena using these indices. Okay, tropical rainfall measuring mission is also a good, in my opinion, it's a good instrument which allowed us to estimate precipitation and use it in order to follow drought, especially in the case of the area when we don't have enough meteorological station. The correlation, it isn't perfect, but it is sufficient in some areas, less sufficient in some in other areas. So we have to be careful about this. And the idea is, since we talk about agricultural drought, meteorological drought, hydrological drought, socioeconomical drought, the idea is to have a dashboard based on more than one indexes in order to follow in space and time and have like an early warning for drought. So 2 minutes? Okay. I think we will just give another example quickly. We'll pass quickly here. In the case of landslide, the Earth observation satellite can contribute also by the production of some important parameters like land use, fault, hydrological network. And here we have an example of probabilistic conditional assessment. We talk a lot about probabilistic modeling, but probabilistic conditional modeling is also important. And I will stop here. Thank you for your attention.
Good morning, ladies and gentlemen. I've been given 10 minutes. The other presenters have eaten my 5 minutes. Let me introduce myself because, in fact, I'm not Tesfaye Korme. My name is Hussein Farah. My colleague Tesfaye Korme had to leave late last evening to attend to some urgent matters, and I had to step in. And I told him, although your presentation is early warning, you have not given me an early warning to do this presentation. But let me give it a try. Let me first present something about the Regional Center for Mapping of Resources for Development. And after that, I will give you our experiences in early warning in 3 different areas. One is on droughts, the other is on flooding, and the last on landslides. And our experience is longer in that order. We have a long experience in drought monitoring. Next is floods, and a bit of little experience on landslides. But let me just first, because I think many of you might not know about this center, we are an intergovernmental organization. We are owned and managed by 18 African countries. In the Eastern and Southern African region, the countries that you see in green are our member states. And our main mandate is to promote the use of geoinformation and allied ICT services in all sectors of national development. And we undertake our mission and mandate through 3 areas that we try to promote and build capacity of institutions in our member states. One you have heard a lot about is Earth observation and its applications, GIS analysis and decision support capabilities, and thirdly, data and information dissemination. And through these 3 main tools and technologies, as I said, we provide or implement our mission and mandate mainly through these activities. Because of time, I'll move quickly. In fact, our major activity is training, capacity building, and our focus is on short-term, practical, skill enhancement trainings. For the target group are people already graduated from universities who are working in national institutions in different sectors. And we provide these other services. And of course, today we are working on, or the topic is on early warning and floods and famine. I will skip this because I think we've had droughts and floods are the major disasters. And here I think we're just trying to understand or be on the same page on what early warning is, because it means different things to different people. But there are those 4 key elements: risk knowledge, risk understanding, which we use Earth observation, monitoring and prediction, which use the GIS tools and models, and information dissemination. Let me start with drought, the easy one. In fact, the lead time we've had from Monday from ICPAC, our colleagues, that you can, using weather predicting models, focus or warn people in good time, let's say even 8 months before. And the What we use Earth observation, the previous speaker very well demonstrated and presented the different vegetation indices that are used, that we can get, every day, every week, every 10 days, to clearly monitor and indicate where the hotspots are. Sorry. And clearly monitor the progression of crop growth and have some indication months before the harvest whether we'll have a good harvest or not. What I want to say here is that, in fact, these are methodologies, procedures that are no longer just on a research basis, but operational. And our colleagues, I was expecting them here from FuseNet, in fact, use this in many different countries, together, of course, with other information, ground information, and produce bulletins, monthly bulletins that are available to our national institutions to clearly indicate the indications of drought. This is what happened last year, 2011, the severe drought in the Greater Horn of Africa. And one of the indices, the many ones that have been mentioned earlier, is on evapotranspiration. And this clearly indicates, the graph there below might not be so clear. 2011 had the lowest, on average, 6 months, evapotranspiration, relative evapotranspiration, which is an indicator of, water availability or moisture availability and plant productivity. It's a combination of the two, transpiration. And that was clearly recorded progressively during the growing season. In fact, this was in July, I think, which shows, and the most of the severe drought came much later in September, October, November. What we're also trying to work with our partners, specifically the JRC, there's a program called Monitoring of Agricultural Resources, which are trying to understand these new methods, techniques, technologies, and use them in our training programs and outreach to our member states. So it's not only a drought, but even when there's no drought, we need better statistics on crop yields, crop statistics on harvests, so that we can prepare better. So remote sensing, meteorological data, the modeling, the crop growth models, statistics, in fact, can be used to improve the current statistics that we have in our countries. And there are these bulletins that are produced monthly, at least for the Horn of Africa, by JRC, Joint Research Center of the European Commission. And what we have been trying to do is go to the next stage of improving crop statistics by actually going to the regional or sub-regional areas, like here is in Kenya, the different provinces in Kenya, where you actually give quantitative estimates of crop yields, specifically maize. We've also been working with the World Bank on the open data, and we have last year quickly got together during the height of the crisis to put the different information from different institutions together, so that the organizations involved in relief, organizations involved in supporting the hunger issue in the region could access information in one portal. And we're trying to improve on this. I've just mentioned one hazard, and I've been told my time is almost up. So I will go through very quickly the flooding. We're working with NASA and other partners, universities within the region and in the US, specifically Oklahoma University, to help us improve at the regional level potential for flooding, and also at specific or local levels, high resolution models. And one was mentioned in Namibia, CREST model, which is working now for the East African region. In terms of early warning, this was the floods in 2010 in Kenya, where we could clearly see, we have these maps on daily basis, which warns potential flooding, whether it's moderate, severe in different places, and the red means is potential for severe flood. And in fact, there were floods, and we were asked by local institutions to activate the international charter that I've already talked about. And we were able to, within 48 hours, produce maps. These are radar map, because during the floods it's normally difficult to get optical data. And the black is water. And you see most of the flood, in fact, is away from, in fact, the river. Major floods in May in the lower Tana River in Kenya. On landslides, we are little experience on this, but we did in 2010, together with other partners, UNOSAT, and with our partnership with NASA, we're able to task a particular satellite called Earth Observation 1, experimental satellite of NASA, to also contribute to the effort to map the areas that had these mudslides. And these maps were produced. And I think I will just stop here with some of the challenges that we expect in early warning. And some have already been mentioned. Earth observation or satellite imagery is not a challenge. In fact, the challenge is inadequate and accurate data, in situ data, ground data, to calibrate our models from Earth observation. And we really need to invest while we're also looking at Earth observation, to invest in ground monitoring systems. Thank you very much.
I note now it's 10:30, so it's time for a coffee break, but we should allow some questions and possibly discussion. So if one of you have anything to ask, we are ready to respond with all the panelists sitting here. You can come to the desk if you want. So you have a question? You have several questions. Is there a microphone for people having questions? Yes, there is a microphone. Here is the microphone. This lady? Okay.
I would like to go. My name is Dr. Jane Mosselin, and I work as a senior consultant on disaster risk management for UNDP. I would like to congratulate the session by bringing to us what most of us already know, with few things. The satellite, the use of space technology for disaster management. However, for those of us that work in development and actually trying to bring back the lost livelihoods of affected population, we use satellite image. And I haven't seen in any of the sessions here, in any of the papers presented, the human part of the use of the satellite image. And I can provide you excellent examples, which is not the case right now, we can do later, privately, in which we had to use satellite image to actually knowing how many of the 2,500 people, fishermen, that lost their boats and fish nets and etc. because of a major hurricane in the Caribbean, category 5. Well, we had to use satellite image to know the amount of silt in the ocean. UNDP requested that we retrain 2,500 fishermen. You can imagine how much money this cost. So, a combination of a group of marine biologists to identify the amount of silt in the bottom of the sea. By using the satellite image, actually we retrained the people and we didn't buy fisher nets and boats. Anyway, I would like to put that point into the panel.
Do you have a question?
No. The question is if you have the human interface in any of your presentations.
All right. So maybe I give a quick reply from the viewpoint of emergency response, not all the aspects of the presentations today. For the charter, the goal of the charter is to meet the requirement of the user, and the users are very well defined. It's the authorized users, the civil protection agencies, and they have clear requirements. And their mandate is to help in the relief response. And this is translated into requirement for geoinformation, and we meet these requirements. Then they use the data, and they use the data to help people. And the focus on the human is key, absolutely. And it's not really shown in the presentations because we try to explain how the satellite data can be used. But clearly, you're right, the human is at the center. The two main interfaces of the Charter for emergency response are the national civil protection agencies and the UN. With the UN, we work with UNOSA and UNOSAT. And for UNOSAT, we have clear examples of utility reports, feedback from users, that the UN teams using the geoinformation are using that in their operational work, trying to support these actions. So I think they try to do what you say, but you're right, they would be better placed than us as recipients of geoinformation to explain how this is used to help people. We're here to explain how it's made. That's why. But your point is correct. Anybody wants to add something on these points?
Yeah, maybe just to say, I think the human aspect is everything which we do in any case. So I think what was presented here is just some of the methodologies which are used in doing that. But ultimately, the final goal is to obviously to see how livelihoods are being improved or how they are being saved in the process.
I think, having said all of this, the goal of satellite here is not to support directly the relief action. It's to enable. It's enabling technologies. I think it would be overselling to claim that with the satellite technology you save lives or you really do a direct action in the relief work. We help people with tools, and these people do the job, not us. Yes.
Yeah, let me just add to that. I think that's an important question, and I think the basis of geoinformation is to benefit society. And I think that is the main principle of all geoinformation organizations, to benefit society. And in fact, even those benefit areas have been defined. And I think I put up one of the slides on that, in all the different sectors of societal needs. Thank you.
There is another question?
Thanks. I think I have a question, I think in particular to Anna Burzikowska about your presentation. You mentioned somewhere that you had a few pilot projects in which you also did some flood modeling with the Earth observation data. And now yesterday we had a whole lively discussion in the flood session about, can you actually use Earth observed elevation data for this purpose? Because in particular in flat areas they are relatively inaccurate. Mm-hmm. And I was wondering, what are your experience with it, and how do you foresee that this may improve in the future? And that, especially the last question, is also a bit to the people that on the ESA side and the NANSA side. Is there any improvement expected on that?
Yes, a very good point. We are actually in the process of assessing the utility of the information provided in the framework of this project, and we are assessing the utility working with the user organizations in the countries when those projects were implemented. And for example, for the flood simulation, which is very often based on the satellite-based digital elevation models, the feedback that we got from the users was that it actually would require higher level resolution to come up with the accurate assessments. But nevertheless, in the areas when no other data exists, no other information exists, the satellite-based digital elevation is actually quite useful to provide some approximation in terms of the exposure. But point taken, for floods, the higher resolution digital elevation models are more desired, are more useful than as observation-based models. Yeah.
Perhaps to add on it, a particular point is also the vertical accuracy of these elevation models. Can somebody comment on that? It's not just the horizontal resolution, but the vertical accuracy that's also is very important.
I think it's absolutely correct. The hydraulics application, which is not hydrology, but the specific bits of hydraulics requires metric or submetric vertical accuracy. And today you don't do that with current DMs. From space data. We do.
It is not so much the absolute accuracy, it is the resolution, the relative accuracy between adjacent cells. And we are very concerned that when people speak about getting better SRTMs, they refer to bringing it down from 90 meters to 30 meters and to 10 meters. And that's not what the hydraulics people want. The hydraulics people want that the vertical elevation is better defined. And we try to look at 10 centimeter and okay, as that example that is now getting, but we get horrified when we hear about models with the vertical resolution of 10 meters, because you can do in some areas, it depends on the area, but in some areas you can't do anything with that.
Another question at the front.
My name is Srimal Samansiri from Disaster Management Center, Ministry of Disaster Management, Sri Lanka. Few years back, we have also initiated a program with Sentinel Asia and through the Japanese government, through JAXA. And what I found is that lead time of the activation and the data collection, rather receiving the raw data and the processing. Anyhow, this takes at least 2 days time. I think I would like to see our experiences from the African region. How is this lead time? How did you manipulate this data within short period? And how is the efficiency? So commonly, anybody can answer this one. Thank you.
You want to, should I say something? I think it's a question to African partners, not to me. So I should not.
Yeah, thank you.
Guido was.
Our experience is that it can improve a lot once you have direct contact with the space agencies. And then you are looking at between time of acquisition of the image and getting it in your computer between 12 and 24 hours.
Just maybe a technical answer to the question. For sudden events where you trigger the charter, and it was not plannable, it's a non-planned event, what you need to do is to do a rush tasking of the satellites. And the charter is a virtual constellation. Each EO mission has its own rules and procedures. Some of them have a tasking time that is very small, short. Some of them have a systematic methods, and you can only upload new inputs once a day or once every 2 days. So the answer to your question is the performance of the sum of all these systems. And we measure that every year. We see how it evolves with new missions. And today we know that within 1-2 days, we get the first data for a call. And we know that with the new planned missions, like Sentinel-1, that will be a washing machine, it will produce the images systematically without any order. You don't need to order the data. So the time to access the data will go down, and it will be better than 1 day with the sum of all the available satellites. Then you need to add up the time to generate the scene from the raw data, which is a few hours, and also the time to make a space map from these products. And today this is half a day or the third of a day to the space map from a level 1 product. So let's say in 5 years, You can say that the virtual constellation for disaster response will have a typical time of 1 day or 2 days, going below 1 day within 5 years. You're welcome. As long as you don't like coffee, obviously.
just one. Very different. The previous question was a bit technical, I think. Perhaps for Hikam is your name, I think. I was wondering, you showed a number of satellite-based indicators for drought, and I was wondering, do you have a feeling who on the ground actually uses that information to make decisions? And is the information appropriate for people on the ground to make decisions? And if so, what type of decisions are being made?
So in the case of drought, of course, we have more than 300 indexes, and maybe an indexes can be good for an area and not good for the other. So in the case of Morocco, since we don't have a good network, ground network, so the government now use this information in order to monitor droughts in space and in time, and in order to know which districts are more exposed and more concerned. Before to do that, this aspect was done with no great methodology. It's done by just some statistical, some sampling, which are not very exhaustive, etc. Now, the processing of very high temporal resolution, we can have the spatial distribution. And would like to just highlight that since we have 300 indexes, the most important work to be done is to evaluate these indexes in the context, in the context of the country before to use it. Thank you.
If there is no further point to be discussed or questions, maybe Jane, you want to say the last word?
Yeah. I would just like to thank you very much for coming to this session, especially our panelists. I think I'm very excited to see the work that is coming in Africa, and with the new technology and better sensors, I'm sure the results will be even better. I would like to thank the World Bank for organizing this very important workshop, and we hope to see more work, especially collaboration between all our space agencies and the World Bank and everyone who is here. So as you go for coffee, can I please ask all of us to thank our panelists and thank ourselves for coming? Thank you.